All right. So in 4.1 here, we're going to talk about a probability distribution function of a discrete random variable. So first, let's talk about what we mean by a discrete random variable. So again, a random variable is a variable, typically an uppercase letter, that represents a characteristic of interest in a population being studied. So the random variable is literally a sentence which defines it. So for example, we could define our random variable, capital letter X, to be hair color of people 18 years of age and older. So once you've defined a random variable, what is the domain of a random variable? So the domain of a random variable may be categorical or numerical, depending on how it's defined. So remember the random variable that I defined previously as capital letter X, and that's equal to hair color. Then the domain of that random variable would be black, blonde, gray, brown, and so on. So any other hair colors I could think of. So this would be an example of the domain of a random variable being categorical, meaning it's composed of labels. Okay. The next example, we have random variable y, which is the result of a six-sided die. Then the domain of this random variable would be 1, 2, 3, 4, 5, and 6. So I think back in chapter 3, well, that was just the previous chapter, we referred to the sample space, and the sample space was all possible outcomes. So you might think of the domain of a random variable as being like the sample space that we talked about before. Now, this particular random variable, the domain of it has these numerical components. So that would be an example of a numerical domain inside random variable y. To go a little bit more into the notation for random variables, so an uppercase letter represents the random variable. So previously I had used capital X and a capital Y, but the lowercase letter represents a number or value in the random variable itself. So for example, we had defined capital letter X to be the random variable for hair color. Then lowercase x would be any given hair color, or if this was defined as something else, it would be any other number within the domain. Capital letter Y is the random variable, and lowercase y is any given label or number in the domain of Y. We don't have to use X and Y. We could use capital B as the random variable, and then we could identify any element of the domain with a lowercase letter of that random variable. Here we have the Greek letter, boy, I think that's omega, and the lowercase for omega looks like a W. And that would indicate a particular, like a datum in a data set. That would be a particular value in the domain of the random variable omega. So, as an example, if we set capital letter B to be the number of heads when 3 fair coins are tossed, then the sample space of B would be this. Now the domain of B, which is the number of heads, we would have 0 heads, 1 heads, 2 heads, or 3 heads. Now notice that this domain is composed of numbers, and those numbers are discrete, meaning these are counting numbers. So the fact that these are counting numbers makes them discrete numerical values. Let's continue to maybe use this example. So an experiment of 50 trials of 3 fair coin tosses was performed. The table below is the result. The number of heads in each trial were counted. The frequency of each value, lowercase b, in the domain of the random variable b was tallied, and the relative frequency of each value in the domain was calculated. So here we have each value in the domain of our random variable. And in the column next to it, we have the frequency for each value in the domain that occurred out of 50 trials. So 8 times we had 0 heads, 19 times we had 1 head, 18 times we had 2 heads, and 5 times we had 3 heads. Now, knowing the frequency for each value in the domain, we can calculate the relative frequency for each value. So this is like the probability of a single event. So we had 8 out of 50, which gives us a relative frequency of 0.16. For rolling 1 head, that was 19 out of 50, or a relative frequency of 0.38. For 2 heads, we got 18 of them, and 18 out of 50 is 0.36. And for 3 heads, we had 5 of those, so 5 divided by 50 is 0.10. And you'll notice that if we sum up, if we add all these together, then all of these add up to 1. So the sum of all the relative frequencies is equal to 1. All right. So let's keep going. This leads us to the definition of a discrete random variable. So for a discrete random variable, the domain of the random variable are countable, meaning they're discrete, and the outcomes are random. So here I've got some examples of discrete random variables. So previously we defined random variable b to be the number of heads when 3 fair coins are tossed. And so the domain of that random variable was 0, 1, 2, or 3. So those are countable. And lowercase b would be equal to one of the values in the domain. We could have random variable x, which represents the number of children in a family. And so the domain of x would be 0 children, 1 child, 2 children, and so on. These are countable values. And we'd use a lowercase x to represent one of the values in the domain of our random variable. We could define random variable f to be the Friday night attendance at a theater. And so the domain of that random variable would be that there were 0 people in the theater, 1 person in the theater, 2 people in the theater, and so on up to maybe the occupational capacity of the theater. And we would use a lowercase f to represent one of the values in the domain of the random variable. And this might be the number of people on Friday, June 8th. And so we don't have to limit ourselves to the English alphabet. We could use Greek, which is not uncommon. And, it helps to maybe use random variables that kind of represent something about the definition. We could use capital A to represent accidents. Okay. All right. So let's go ahead and stop there with that definition. Let me know if you have any questions.